Just a quick thing before I forget, in case I forget at the end of the day. Even though Monday is Columbus Day and everything else, the college is open. So while other things might be closed, we're still open. We'll have class. All right. So on Monday, we were looking at the beginning of probability, and we were looking at some basic definitions of probability and types of probability. And we also looked at some of the addition rules for probability. So today we're going to look at multiplication rules, and then the combinations and permutations towards the end of class. So when we're looking at probability, most of the time when you're seeing probability, you're going to be looking at it in terms of one thing. You're going to be looking at this event or that event. However, there is certain situations where we have what's known as conditional probability. And that situation is where we're given something to begin with, and then we want the probability based on that given. So, for example, if I wanted to find the probability of a male wearing a black shirt in the room, I would count up all the people in the room. I'd count up the males who have black shirts on, and that would be the probability. However, if I say, given that I'm picking a male, what is the probability that they have a black shirt on? That now changes things. So that's going to be my bottom number that I'm going to divide by is only the males, because that is now my group I'm looking at instead of the entire class. And that's what's known as a conditional probability. Just like with everything else in this class so far, wording is very important. You're going to be looking for that word given, or if this is true, then that, those type of situations. So we're going to look at a few of those. The symbol you need to know is that one. That's the symbol. So if you see that A with the bar in it with the B, that means the probability of A given B. The top one, that is your intersection of the two. And then that is just the probability of B. That's of the given event, actually. Okay, so that's the probability of that given event. As with everything we've done so far, the definition's one thing. Once we actually start working with it, it makes it a little more sense. So you don't necessarily need to write down all the words. Write down this and say the probability of A given B, and you should be fine. All right. So they're doing some market research. This is the information and data that they've collected. So what is the probability that they interviewed a 18 to 34-year-old? Start with that one. What's the probability that they interviewed an 18 to 34-year-old? So how many 18 to 34-year-olds were there? And then for probability, we're just taking that and we're dividing it by the total number of people they looked at. So 1403. That would be the probability that I chose an 18 to 34-year-old out of the entire group. You're going to notice more and more of these, we're going to use fractions for a lot of the calculations just because they are simpler to work with. I know people don't like fractions, but trust me, in a lot of situations, they're going to be easier to work with than going to decimals, especially when we're looking at some things that are going to get very, very small decimals or very, very small percentages. So that fraction makes your life a little bit easier. And that answer is the same as if you sat there and did the division, which you would have had to type that into the calculator anyway, so save yourself the extra step. unless it specifically asks for a decimal. All right. What is the probability that an 18 to 34-year-old liked the product? Right, 213 out of the 1403. Okay, because there's 213 18 to 34-year-olds that like the product out of the total.
Wouldn't it be 550?
The question is now, it's where is there a given? And my statement that I said, what is the probability that an 18 to 34-year-old likes the product? I didn't say, given this, what's that? So that's still out of the whole total. Okay, so there's 213 out of the 1403. If I said, given an 18 to 34-year-old, what is the probability that they liked the product? So now we have that qualifier. We have that conditional probability. I'm telling you, I've chosen an 18 to 34-year-old. What is the probability that they like the product? In that situation, it is going to be 213 over the 513. Because there's 513 18 to 34-year-olds I've chosen out of that. What's the probability that I picked one that liked it? It's 213 out of the 513.
So what's the total down at the bottom saying?
That's the total that liked. So if I said the other way, if I said given that the person or the product was liked, what is the chance that they were a 50-year-old? That's 144 over the 550. So that's the one I'm looking at. That's the given. I gave you 18 to 34-year-olds. The total is 513 18 to 34-year-olds.
So I don't understand the column going down then.
That's the like. That's the ones. That's the liked group. Those are all the people who liked it.
Okay.
That's the total of the number of people who liked it. 550. So if I said, given that the person does not like the product, what is the chance that they are over 50? That is the 219 over 600, because I'm now looking at that was the given. I said, given that the person does not like the product, so that's the given, so that's the group I'm looking at, what is the chance that they're over 50? That's the 219 over 600. What's the question?
Why wouldn't it be 446?
Because I'm giving you not liked. I'm telling you that they don't like the product. Okay, so that's what I'm telling you. So that's the group that we're looking at, is the not liked. 446 isn't not liked. 446 is over 50. 446 is not in that not liked column at all. Not liked is up and down.
Okay,
So I'm saying that there's, out of the 600 people that don't like the product,
440 is 208.
over 50 is 219. So that's what that would be. If I know the person didn't like the product, there's 219 of them that are over 50. So that'd be the problem. That'd be the chance that I'd pick one of them. That would be that probability. Okay. So it's all about the order of the words. So the question on the screen says, if an individual is between 30 and 50, so now they're giving you that information, right? They're telling you that we're looking at the 35 to 50-year-olds. So we're looking at this row. What is the probability that they will like the product? Right. That's 193 over 444. Okay. So the given tells you which information you're looking at. And then you look at the piece inside of that for the top number. Because that top number is the intersection of those two things. And that's the intersection of both the liked and the 35 and 50. That makes sense? Let's look at another one. This one's not a table, so it might be a little bit easier with less numbers. Out of 300 applicants for a job, 212 were male. Of the male job applicants, 110 have served in the military. What is the probability that a randomly chosen applicant has served in the military given that they are male? $110. Yeah. Okay. So given that they're male, there's 212 that's male. So that's the bottom. That's the total that I'm looking at. On the top, we're looking at, well, there's 110 that served in the military. There's 110 males that served in the military. So it's 110 out of 212. So the given that's male, that's how many males there was that was in the job applicant pool. And then that top number is how many of those were in the military. If 152 of the applicants had served in the military, what is the probability that a randomly chosen applicant is male? Right. So now the given is the ones that are in the military. So in this case, the given is 152. That's how many were in the military. That's the given. The overlap or the intersection of those, there was 110 that were in the military and male. So it's 110 over 152. Yes. Were you asking a question or were you just holding your hand up?
No.
Okay.
No, I get it.
Okay. I can't tell sometimes. Sometimes people like do this and it's like, I don't know.
No, I'm sorry.
You're fine. You're fine. All right. All right. Actually, we're going to just scoot up to here because we don't need the other information. All right. Suppose that the probability of a caller reporting the system lockup. So this is a customer service helpline for a computer. And they're looking at report the calls. So it says, suppose the probability of a caller reporting a system lockup is 70 or 0.7. The probability of a caller having problem A, there was 4 different options, A, B, C, and D, and a lockup is 0.6. So what is the probability? So given that the caller reports a lockup, so what's the given? Right. That's the given because they're reporting a lockup. What is the probability that the cause is A? So what's the overlap between lockup and A? 0.6. So that's 6 seconds. What's the probability that the cause of the malfunction is not problem A, given that the caller is experiencing a lockup? Why? It'll actually be 1/7, but why?
Because if it's not A,
Well, that would be 0.4. Right? Well, it's the opposite because it goes to 1, right? So that'd be 0.4. Okay. So if we look at, this is a Venn diagram, right? So A, so that's A, that's lockup. That right there is the 0.6. That is 0.4. That's for all of A, right?
Where are you getting 0.4?
A would have to add up to 1, right? The probability of A would have to add up to 1. What's everything? In probability, what is everything? Right.
100%.
It's like 100%.
Okay.
So that's 60% and 40%. Okay. So, but does that tell me anything about B, C, and D? No, right? So it's not the 0.4. If the person's calling up and they're saying that they have the problems causes A, that's 6/7, right? What is the opposite of that? What is the complement of that? So if they call up and report a lockup, what's the probability that it's A? It's 6/7. So what is the opposite or the negative of that statement? If they call up and report a lockup, it would have to be either B, C, or D, right? That's the opposite of it, or the complement of it. So if that's 6/7, complement is always 1 minus, which you have. So 1 minus 6/7 would be 1/7. So that would be B. So the opposite of them calling up and saying that the problem is A is the problem is not A. And that'd only be a 1/7 chance. Okay. That's they purposely do that question to make you think about the concept of it and everything else. So remember, probability, everything always has to add up to the 1. So if you have one statement and the opposite statement, those two have to equal 1. So if I was setting up the call center, my tier 1 support would always be dealing with A. I wouldn't even teach them about B, C, or D because, and then B, C, or D, if it's anything other than A, just send it to the senior tech and they'll deal with those because only 1/7 of the time that it's going to go up. All right. We talked about mutually exclusive events on Monday. Mutually exclusive events are two events that do not overlap each other. There's no intersection in that respect. Another one that's similar to that are when two events are independent. There can be overlap in terms of an intersection, but two events that are independent do not interact with each other. They don't have any impact on each other. So if I'm going to look at the conditional probability of these, it would actually just be equal to the original probability because there is no overlap in that respect. The B in that respect is exactly the same as it would be the total. So it sounds more complicated than it really is. The easiest way to think about independent events would be if I'm flipping a coin and I'm rolling a die. Do those two events interact with each other? No. Flipping the coin has no impact on rolling the die. Those two events are known as independent. If the two events are independent, to figure out the probability of those events happening together, I just multiply those probabilities together. Okay. So, what is the probability that I get heads on a flipping a coin? 1 out of 2, right? So this is where using fractions are really going to help you more than using decimals. So like flipping a coin, simple. It's 50-50, right? 50%. However, if I say, what's the chance of you getting an ace of spades? It's way easier to say 1 out of 52 than whatever the percent's going to be. And you want to be consistent because when you're putting things together, you don't want some to be percentages and decimals and some to be fractions. So it's easier just to do everything as fractions. I know you guys hate fractions. Everybody hates fractions. I get it. But it'll definitely be easier for you to do your calculations with fractions. So the chance of me flipping a coin and getting heads is 1 out of 2. What's the chances of me flipping 2 coins and getting both heads? It'd be 1 out of 2 for the first coin, right? And it'd be 1 out of 2 for the second coin, correct? So it'd be 1 out of 4. Okay. Each one, are those two events independent? Did the first coin flip have any impact on the second one? No, they're completely independent. So we would just multiply those probabilities together. So the chances of me getting 2 heads is 1 out of 4. If you remember, what's the chance of me getting 3 heads? I would multiply it by 1/2 again. And that'd be 1 out of 8. And if you remember from Monday's class, we did that list of the coin flips for 3, and there was only one of them with heads, 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 and there was 8 total options. Okay. So if I was looking at getting 100 heads, it'd be 1/2 times 1/2 times 1/2 times, it'd be 100 times. It'd be a really, really tiny amount, the chance to be getting it. Is it 0 though? No. Remember we said if an event can never happen, it's 0. Getting 100 heads in a row, very, very, very unlikely. Not 0. Okay. All right. What if I flipped a coin, rolled a die, and drew a card? This is where I said using fractions is going to make your life easier to work with. What is the chance of me getting a tails on a coin? 1/2. What about getting a 5 on a die? That's 1/6. And what about a jack of clubs from a deck of cards? 1 out of 52. All right, I'm going to remind you how to do fractions. How do we do fractions? We just multiply straight across. So 1 over, and then we multiply the bottoms. So the chance of getting all 3 of those is 1 out of 624. And it's obvious that all those are independent events. They don't impact the other one. So like the first couple, like this one, 50-50, this one would be 0.167 or 6666. That would be pain. 1 out of 52 is a really small number. That'd be a pain. So it's way easier to do it this way and just leave it as a fraction. You do not need to necessarily get it as a decimal. Skip that one. All right. Oh, that's class took too long. In a production process, a product is assembled using 4 different independent parts. A, B, C, and D. In order for the product to operate properly, each part must be free from defects. So all 4 parts have to work for the product to work. The probabilities of the parts being non-defective are given by this. So probability of A is 90 or 0.9, B is 0.7, C is 0.8, and D is 0.9. Okay. What is the probability that all 4 parts are defective? I want him to think for 1 minute. All right. What's the probability that all 4 parts are defective? How would we figure that out?
You have to find the complements of the non-defective probability.
Yeah, in this case, I need to find the complements first. We don't have the defective number, right? We have the non-defective number. And these are small enough, these are simple enough, we can leave these with decimals. No, I know. So when I say write things as fractions, I don't change decimals to fractions because that again adds more work. Use what they give you, but if it's not given to you, a fraction will definitely be easier to work with. This one, a decimal is just as easy to work with. So we're going to take the complement of each of these. So the A is going to be 0.1. The B will be 0.3. C 0.2 and D 0.1. All right. So now what's the probability that they'd all be all four of them will be defective? What do we do with those four numbers? We multiply
Where are you getting these numbers?
right here, subtracting them from 1. The complement is 1. So 1 minus 0.9 is 0.1. $1 minus 90 cents is 10 cents. So we have 0.1 times 0.3 times 0.2 times 0.1, which 0.0006. All right. What's the probability that the product will not work? All right. Let me ask a different question. What's the probability that the product will work? How do we do that? For it to work, they all have to be right, right? Okay. So if I was just going to multiply them all, that would tell me if it worked, correct? So how would I find the probability that they don't work? That it wasn't going to work? The complement of it. I would just do 1 minus whatever number I got. Okay. I can't, what they wanted you to do was do 1 minus the 0.0006, which would be wrong. Because that's if they all are defective. And if any one part's defective, it won't work. Okay. So we really need to find out is what's the probability of it working and then minus that from 1. So I would do 1 minus the 0.9 times 0.7 times 0.8 times 0.9.
0.4536.
Is the 1 minus it or no?
No, sorry.
Okay. So if you 1 minus it, I think it was 0.5 something, right? Hold on, I have it on my calculator.
0.5464.
Thank you. So that's the chance it's not going to work. I probably would not buy this product. Okay. So again, when you're doing these problems, a lot of it comes down to reading what they're asking you for. Okay. It's not always going to be just take a couple numbers, multiply and get the answer. So we have to really think about what they're actually asking you. All right. What about this one? What's the probability of drawing a king and then a queen from a standard deck of cards? All right. Every one of these problems, let's break them down into pieces. What is the probability of me drawing a king out of a deck of cards? 4 out of 52. It's 4 kings, 52 cards. What is the probability of me drawing a queen out of the deck of cards? Right. So there's a key word here that we haven't talked about yet. Without replacement. If I've already taken the king out of the deck, okay, how many queens are left in the deck? 4. How many cards are left in the deck? 51. Okay. Because I've taken the king already out of the deck. So, are these two independent events? No, they are not. These are not independent events. Okay. So, these events, when you look at them, they have an interaction to each other. So that means my bottom number is going to change, or some of my numbers are going to change. So in this case, when I multiply these together, I get 16 over,
8,600.
thank you.
Yeah, you're almost right,
Did you divide that real quick for me? Okay. Because no. But it's one of those ones that I wanted to show you the number because this is where fractions are great. However, most people don't work with fractions on a regular basis. So I said 16 out of 2652. You're like, how's that compare to things? By me telling you it's 0.006 or 0.6%, it's like, oh, that's not very common. Okay. So that's if I drew a king and then a queen. What if I wanted to draw two queens? What's the probability of me drawing the first queen? That'd be 4 out of 52, right? What's the probability of me drawing the second queen? 3 out of 51. I have one less queen and one less card in the deck. What's the question you have? How many cards are in a deck? Right. How many kings?
There's 4.
Right. That's how I get the 4 out of 52.
But you're saying there's only, if you pull one king,
Yes.
one queen, one king out of 52.
Right.
One queen, there's 51.
Right.
But you have 4 kings.
I'm not, no. So how many kings are in the deck? There's 4. So my probability of drawing a king is 4 out of 52. I'm only taking one of them, yes, but my probability of getting that king is 4 out of 52. Okay. Let's think of, let's,
Go on.
no, let's,
No, because it's not a big deal. I don't get it.
no, actually, it is a really big deal. That's the point. That's the thing. It's understanding because my last class had an issue with the question 2 questions from now. That was exactly the same concept. If I was going to roll a die, okay, and I want an even number, okay, I only want one even number, correct? I want it to come up an even number. What is the probability that's going to come up an even number?
There's 6 sides on a die.
Yep, and how many of them are even? 2, 4, and 6. So there's 3. So my probability that I'm getting an even number is 3 out of 6, right? Not 1 out of 6, even though I only wanted one number. When I roll the die, it's only going to come up one number, correct? But the probability that it lands on an even number is 3 out of 6.
Okay, so now.
That's where the king comes in. I'm only pulling one king, but there's 4 kings in that deck. So the probability of me drawing that king is 4 out of 52. I'm not looking at the one I'm pulling. I'm looking at the probability that I'm going to pull one out of the deck.
So on the second line, you have 4 queens.
Yep.
And then you have 3 queens.
Correct, because I already pulled one out. So I pulled a queen out. I set it on the table. How many more queens are left in that deck?
But you've already pulled a queen, so why isn't there 50?
This 2 different problems. 2 different problems. 2 questions.
Okay.
So this question is the 2 separate questions.
Okay.
So the second queen was 3 out of 51 because there's already missing a queen and I've already pulled a card out of the deck. Okay. And then if I multiplied those, it'd be 12 over 2652. So it's harder to than it is to pull 2 different cards, which should make sense because that's why a pair is worth more when you're playing games. Okay. And it doesn't matter king or queen. Like if I said this was a 2 and a 5, do these probabilities change? No. So if it was a 2 and a 5, it doesn't make a difference. There's still 4 and 4. So that probability right there is the same for picking any 2 cards out of a deck of playing cards. Okay. It's harder if it's the same card you want. All right. Do this one real quick.
There's 13.
Yes, there's 13 of each suit. All right. How many ace of spades are there in the deck of cards? 1 out of 52. What's the chance of me pulling another spade? There's 12 other spades out of 51. So it's 12 out of the 26, 52. Oh, we did, yeah. Doesn't matter. Mm-mm. Oh, if yes. Yes, that would not be a random experiment then. Remember the whole concept that we said at the very beginning when we started probability, right? It has to be a random experiment, correct? Okay. So if you don't shuffle the deck of cards, is it a random experiment? No, because you can predict what's coming next. Remember I said at the end of last class, it is assumed that all these are random experiments. Otherwise, none of the stuff we're talking about makes sense. It is a good question, that you have to be specific, but yes, we would assume that they're random experiments. So we spent all the time in determining if they were random experiments. All right. Yeah, we're not gonna skip that one. Okay. I might go back to this problem, but all right. So we've looked at being able to find probability, but what's the bottom number is the most important piece, right? Like when we're looking at this, that bottom number, we need to know how many there was to choose from. So the fundamental counting principle actually allows me to start coming up with how to find the number of options that I have. So let's think about your phone number. We're going to ignore the area code for a minute. Okay. How many numbers are in your phone number without the area code? 7. I'm old enough to remember when you didn't have to dial the area code if you were in the same area. Now you have to do no matter where you are. Okay, so we've got 7 numbers. We've got 3 digits and then 4 digits. How many numbers can be in the first one? How many different numbers can be the first digit? 10, right? There's 10 numbers on your phone, right? So 10. How many is in the second one? How many in the third one? Fourth? And it's all 10, right? So how many different phone numbers can I have? We're going to multiply these. So yes, 10 to the power of 7. So there's a possibility of 10 million different phone numbers for one area code. Okay. Does that make sense? Because we could have all the numbers from all 7 zeros all the way up to 7 nines and every number in between. There's 10 million possible combinations. So, however, in phone numbers, there's a little bit. So the area codes are based on your state. And we currently have 4 area codes in the state of Connecticut. I remember when there was just one. That's how old I am. Actually, the entire state was 203 at one point. 203 was the original area code for the state of Connecticut. Then they added 860, then they added 417, and I think it was 908 was the other one. Somebody told me in the last class. So, yeah, 417 is the western part of the state, and I think 908 is the side of the state. So the next 3 digits actually are your location. It actually is based on where you lived. So it would like be a community, because way back when the telephone system first started, the operator literally had to plug in wires to connect your phone call. So when you called an area code, when they started putting the area codes and stuff in that place, a computer was flipping those switches. So the area code meant it went to that computer, and then the system went to that computer and it would route it through. So the only actual, the last 4 digits were the actual random ones. Other than that, they were all very similar in the area. So that's why we have to actually keep adding area codes, because there's not enough numbers to fit all the house. Well, the house phones are gone away, but those house phone numbers still exist, even though we don't actually use them. There's everybody's cell phones, fax machines, computers. There's phone numbers for a ton of different things. So that's why we have so many phone numbers now. But that's how we'd figure that price out. That's the fundamental accounting principle. We're always going to multiply those out. Let's look at a license plate. This actually is how Connecticut's were done too. So 3 numbers followed by 3 letters, excluding I, O, and Q. Why would they exclude I, O, and Q?
For 1 key.
Because it's really hard to, when you're thinking about a cop, who's the people who are looking at your license plates, it's really hard to recognize that little tiny thing under thing. And it looks like an O. You can use them in personalized plates, but most of those times they actually can tell what it is based on a personalized plate. So, all right. So let's see. We're going to look at the same boxes. We have the numbers over here and the letters over there. So how many numbers can go on the first one? 10. How many numbers can go on the second one? Third one. How many letters? How many letters do we have total? 26 minus those 3 is 23. So how many total license plates were there? So multiply them all together.
12,167,000.
Good. Now Connecticut went to, what's the license plates in Connecticut now?
7 numbers and letters, something stupid like that.
2 letters and 5 numbers. 7 digits now. They actually went from 6 to 7. So did we increase the number of license plates? But we decreased the number of letters, right? So it's 23 and 23. And then we have 5 more that are 10s. Apparently I didn't save that one.
Do we also exclude the I and the Q?
Yeah,
You did too?
they all did. It was believe it or not, states don't do things on their own. They all communicate, because if you go to another state, the cops are gonna have the same problem. So yeah. So we can now have 52,900,000 plates. We only have about 3,500 or 3.5 million people in the state of Connecticut. That's total. So I don't think we really need that many license plates. The problem is they don't typically reuse them. So like once you've used the license plate, even though you turn it back in and technically they could reuse it, they don't. So once you're issued a license plate number, nobody else is ever going to be issued that license plate number. So that's why they keep running out of them. Okay. That's the fundamental accounting principle. That makes sense? What's some of the, so when we're looking at these, this is just giving me that total set, but are the numbers, can the numbers and letters be repeated in this situation? Yes. Is it always going to be the case that we want to have the things repeat? No. Sometimes we don't want the numbers to repeat. We only want them to show up there once. There's 2 other ways that we can look at counting numbers. There's permutations and combinations. You will see this in your calculator, typically written like this, NPR. This is another great situation of Hawks liking to use letters that are not standard. Every calculator out there uses the R, and Hawks is using K. So you will not hear me say K. I will always say R. So permutation is giving me a specific order for the objects. So if order matters, we're using a permutation. So if order matters and things don't repeat, like I can only choose it once, it's a permutation. Oh, I forgot. I got to bring Desmos. So on the Desmos calculator, that is your NPR button. Just click it and we're going to type the numbers after it. Your scientific calculator on your phone probably does not have those buttons. However, Google? Oh, Ruguru? Yeah, because actually in Ruguru, you got they have the Desmos calculator built in. Hold on, I'll show you. But you don't even have to log into Ruguru to use this. Just go to Desmos and it works there. So if you go to Ruguru, it's right here. Scientific calculator. There's scientific calculator. Same process. So yes, it is there too. All right. So let's see how we're going to use this. So I've got 7 sprinters advanced to the final heat of a track meet. How many ways can they finish first, second, and third? So first question, can they repeat? First question is, can they repeat? Can the same person finish first, second, and third? No. Okay, so we're not just going to multiply 7 times 7 times 7. Does order matter? Yeah, because first, second, and third are 3 different places, right? And first and third are not the same thing. So order does matter in this situation. A great example of this would be, let's say I'm making a club, and I'm going to pick 5 of you to be in the club. Okay? Does order matter in that situation? No. If I'm going to pick 1 to be president, 1 to be vice president, 1 to be secretary, 1 to be treasurer, and 1 to be the water boy, does order matter? Well, yeah, because president and vice president are 2 different things, right? So they would have different powers. So order would matter in that situation. Where if I was just picking you to be in the club, the order wouldn't really matter. Okay, so in this place, first, second, and third order does matter because those are 3 different things. So we're going to use our permutations. So we're going to use that NPR. So N is the number of people in the race. So total number. R is how many I'm choosing. Okay. So in the calculator, I'd hit the NPR button, and then I'd hit 7,3. And it's 210. You always put the bigger number first, because in essence, it's saying 7, choose 3. I can't say 3, choose 7, because I don't have 7 to choose from. Okay. If you screw it up and type it in backwards, it's literally just going to give you 0, which wouldn't make any sense, because you can't pick 7 from 3. That's why it's 0. So it's always the bigger number first. Yes.
I remember doing this. Is there a way we could do like 7 times 6 times 5? Or is that something?
So, yes. And it will work out. The problem, so it will work, It's just harder to do, especially when the numbers get bigger. Actually, the formula, which I kind of glossed over because I wasn't overly worried about it, that's where your n factorial over n minus k is. So if you have 7 factorial over 4 factorial, that's where the 7 times 6 times 5 comes in, because factorials mean multiplication. So I didn't want to go through that because you're not going to need it, and it's confusing to more people than helpful. So yes, it'd be the same concept. All right. So let's see, do I have another one of these or do I just go to the Mississippi? I just go to the Mississippi. So let's do another one of these. Let's say, how many people are in here? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right, so I got 20 people and I'm choosing 5 for my club for different positions. So will order matter? Yes, because the positions are there. So I'm going to do what? 20 choose 5. So 20 P5. So I go to Desmos. Oh, that's not what I wanted to do. So there's 1,860,480 different ways that I could choose 5 people from this class in different positions. Okay. So lots of different clubs I can make. All right. In this situation, everybody can be chosen only once, correct? In the first situation we did, everybody could be chosen every single time. Like we had the 10 numbers, we said we could choose the same number multiple times, right? Well, what happens if we have a combination of those? Mississippi, the only state that everybody can spell without even thinking about it. All right. How many different ways can I make words out of that? Because the letters repeat, right? So I have 4 I's, I have 4 S's, I have 2 P's, I have 1 M. So the formula for this, when you're looking at this formula, it's very actually similar, except it's not using the NPR and the NCR. It's using that little factorial button, that little exclamation point, which is also a Desmos, and I'll show you that too. So how many total letters are in Mississippi? 11. So I have 11, and that little exclamation point is called a factorial. 11 factorial.
We're not saying anything.
Oh, thank you. There we go. All right, so I got 11 factorial. How many M's are there? So on the bottom, I put 1 factorial. How many I's are there? So I put 4 factorial. How many S's? How many P's? So that's how I set that up. Okay. So the top is going to be how many values you have. Okay. And the bottom will be how many of each of those types. So 1 M, 4 I's, 4 S's, and 2 P's. So now we go to Desmos. On that same screen with the NPR and the NCR, there's a little exclamation point right there. So I'd hit 11, hit that. 1, 4, 4, 2. And that's my answer. Huh?
What is the 34,000?
34,650. That's how many different ways that I can write the letters of Mississippi. Because if I put an I in front, I have 4 eyes. Doesn't matter the other eye, it's still the same eye. So it's not going to be a different combination. Okay. So it's just using that little formula. Exactly what you said. That's how you get the 7 times 6 times 5. That's what a factorial is. So here's a factorial. So 5 factorial is 120. That's the same thing as saying 5 times 4 times 3 times 2 times 1. That's what a factorial is.
I
So,
have a question for you.
yes.
Has nothing to do with this, but why do we need to know this in our lifetime for anything?
I don't know. What are you going to do for the rest of your life?
Criminal justice.
Okay. So then you need to know stats because you're going to be dealing with statistics all the time. Criminal justice is all about stats.
Being a parole officer.
Okay, that's not necessarily criminal justice.
Yeah.
So, but again, you take classes because we don't know what you're going to do. In criminal justice, you can be everything from a lawyer's assistant to going into law to being a parole officer to being somebody who's working in the courts and they all do different things. So that's what your degree opens up, and I need to prepare you for all those degrees. So that's why we learn stuff.
Sorry.
It's fine.
It's just mind-boggling. I'm sorry. Yay.
Last one, combinations. The biggest difference between, sorry, I didn't switch over. The biggest difference between combinations and permutations is, in combinations, order does not matter. Okay, so order does not matter. This is the NCR button. So this is where that wording comes into play. Does order matter or does order not matter? To choose which option is important. Order not mattering should leave you with less combinations. That would work. Because 1, 2, 3 is the exact same as 3, 2, 1, because it doesn't make a difference. They're the same thing. Where if order mattered, 1, 2, 3 and 3, 2, 1 are 2 different values. All right, let's look at the lotto. Everybody hopes to win at some point. So we have the actual same Cash 5 lottery in Connecticut. I don't know how many numbers it's out of anymore. They keep changing it to make the odds harder. So you're selecting 5 numbers from 1 to 38. If you've ever seen the lottery drawn, it's literally a ball pit, and balls get pulled out of the pit. It doesn't matter the order they're coming out because on your ticket, they're always in numerical order. So it doesn't make a difference the order that they come out. So in this case, this is going to be a combination because order does not matter. So I have 5 numbers I'm choosing out of how many? 38. So it's NCR is going to be 38. Choose 5. So 501,942. I know. I wasn't switching over on purpose. That's okay. Because I've shown you how to type it in a few times now, so it's not like it's 42. I didn't change any count rates, how I typed it in the calculator. So what's the probability of winning? The only one that wins is the one that gets all 5 numbers right? So there's only one way to do it. So the probability of winning is 1 out of 501,942. Okay. So this happened in Massachusetts, and I think actually it happened in Connecticut too. If that lottery got to $10 million, okay, and it was $1 a ticket. How much would it cost you to win? Guarantee you're winning. To guarantee you win it. The only way to guarantee you win it is to buy every possible number, right? So you'd have to buy 501,942 tickets. How much did you just spend? $501,000, right? And you just won 10 million. Okay. So, and I know it happened in Connecticut too, but I know the story actually happened. There was a story in Mass too, that the one that I could actually remember. So basically what they did is they had a group of people go around to all the different liquor stores and everything else that were selling them because you had to actually have the actual filled out cards for every possible combination, because you couldn't just do quick picks because you get repeats. So they literally went in with a stack of them in each store and ran them through for like a week before the lottery was going on to buy every single possible combination of the numbers to win it. I think they ended up splitting it, but they still ended up winning more money than they spent. So they changed the rules. They actually increased the odds, so there's more possible combinations. And they actually limited the number of tickets that any one machine could sell in one day to prevent people from being able to do that. If enough tickets are sold, the machine will shut off. And they'll tell you your machine is down for the day. So, but that's where they figured this out and go, oh, okay, I can do this. So right now, so like the Powerball jackpot, I think you have like a 1 in like 300 million chance of winning it. But the jackpots are breaking billions of dollars now. I think one of them was like $1.6 billion. The problem is there's no way for you to buy 300 million tickets. So they've gotten to the point where it's so far out of the realm of anybody even trying to do it but that's what happens when you have a very small lottery like this. All right, let's do a couple. Problems. I need to select 6 songs from a CD containing 12 songs to compose a musical lineup. How many different ways can I do it? So the question you have to ask yourself first is, does order matter? Well, first of all, can the songs repeat? No, you're not going to. 6 songs, if you repeat the song, the DJ is going to get kicked out of the place. So they were probably not going to repeat, so we don't have to worry about that. Does order matter? No, they're just 6 songs. So which one are we using? Combination or permutation? Combination. So it's 12, choose 6. Okay. How many 5-card hands can be dealt from a deck of 52 cards? So can you get the same card twice? No. So that is out. Can I, does order matter? No, because when you get 5 cards, you get 5 cards, right? You can put them in any order you want. So what am I doing? Combinations. So it's going to be 52, choose 5. When order matters. When order matters, I use permutation. All right, last one. Kara was born on 11/21/1992. She wants to make an 8-digit password using all the digits in her birth date. How many different 8-digit passwords can she create? So does order matter? Yes. Order matters. Because if you type your password in backwards, however, things repeat themselves, right? So I'm going to need to use that, the ones with factorials in it. So how many numbers do I have? 8. So 8 factorials on top. And now we got to write the numbers. How many ones? I have 4 ones. How many twos? 2 twos. How many nines? 2. These 3 numbers down here should add to the top number. If it doesn't, you screwed up. Okay. All right, we're done with chapter 8.6. I will see you on Monday.